Welcome back to EasySpin Academy 2020. This is session 15, and in this session we're going to talk about pulse shaping. Just a quick preview for the next 3 sessions. We will talk about interfacing EasySpin with Orca. We'll talk more about simulating magnetometry data using EasySpin's function curry. We'll look more in detail at line broadenings, and we'll also look at coupled spins. And in the very last session, we'll look at simulating EPR spectra for molecular dynamics, some higher order spin operators, and finally, a look behind the scenes of EasySpin, how we test and release EasySpin packages. So in this session, we'll focus on shaped pulses. Pulse shaping has become a thing in the last 10 years or so, and it refers to the fact that nowadays with good hardware one can not just turn on and off a microwave source, but one can actually modulate the phase and the amplitude on a nanosecond timescale and thereby achieve new types of excitation for the spins. EasySpin has several functions that support pulse shaping. First and foremost, there is a function called pulse, which constructs pulse shapes of various forms. The second function is saffron, which then can take these pulse shapes and utilize them to simulate pulse EPR spectra. And the third one is called Spidion, which is a more advanced function that allows you to investigate spin dynamics in a time-dependent fashion in much greater detail and a more granular level of control. So first of all, let's look at some basic usage of pulse. I'm going to start out clearing everything out. And the function pulse that constructs a pulse needs a set of parameters, which is called a par. We need to define them. Par is a structure that collects a variety of fields. First of all, we need to tell EasySpin what type of pulse we want. And we want a simple rectangular pulse, meaning we just turn on the amplitude at time 0 and switch it off at some time later, and leaving the amplitude constant and the frequency constant in between those 2 time points. Next, we set the length of the pulse in the field TP, which is 20 nanoseconds. As usual, the conventional time unit in EasySpin is microseconds for pulse EPR simulations. Then we have to set its frequency, so the carrier frequency of the microwave pulse, and we're going to use, let's say, 1000 megahertz, so a fairly low frequency of 1 gigahertz. And finally, we have to specify the flip angle. Let's make a 90-degree pulse, pi over 2. And as usual, by convention, the EasySpin's angles are in units of radians. So now we can call pulse with these parameters that completely specify a microwave pulse. And if you don't ask for any outputs from the function, it will be plotted. Here's the result. This is a figure with 3 panels. On the left-hand side, you see a time axis and an amplitude, and on the amplitude plotted on the vertical axis with the I and the Q signals that are used to generate this pulse. And you can see there is it's an oscillation, a 1 gigahertz oscillation that has a constant amplitude. It just turns on at time 0 and switches off 20 nanoseconds later. Now the frequency time dependence of the frequency is shown in the middle panel, and we specified 1000 megahertz, and we kept this frequency constant throughout the pulse. And so it's a very simple straight flat line. And then on the right hand side, it shows the excitation profile, and you can see that this 90-degree pulse at 1000 megahertz, takes the spins down from +1, which is here's the magnetization for the Z component, from +1 to 0, which is the XY plane. And you can see that the excitation profile looks quite, similar to a Gaussian. You can also show the X magnetization and the Y magnetization. This is basically just a rendition of where the spin is after the end of the pulse, if the spin starts out on the negative Z or the plus Z direction. So this is the plot you get when you don't ask pulse for any output. And this is a monochromatic pulse without any amplitude modulation. Now let's see how we can modulate amplitude and phase. For this, we're going to define a new pulse, and the one common one is a hyperbolic secant pulse. hs.type equals hyperbolic secant hyperbolic tangent. So here again, I'm defining a new pulse parameter set. I called it par in this previous example, but now I'm just going to call it hs to make it distinct. The type again tells EasySpin about what type of amplitude and phase dependence you want to have. So the first is the amplitude. The first and the second specify the amplitude and the frequency dependence of the pulse. Let's make the pulse a little longer. hs.tp, let's use 0.2 microseconds, which is about 200 nanoseconds. Let's specify a frequency range. Now we want to chirp it. We want to sweep the frequency. We're going to go from -100 to +100 megahertz. That is the frequency sweep rate. Now, these pulse shapes that use the hyperbolic secant for the amplitude and the hyperbolic tangent for the frequency response, they do need a parameter. And for this particular type of pulse, the parameter is called beta. This is a truncation parameter. And finally, we need a flip angle. And the flip angle, let's set it to pi, so let's make a 180-degree pulse. Again, this is in radians. Let's see how this looks like, how this pulse looks like. Pulse hs. I think the flip angle did not work out. I have a typo here. Here is the result. Now you can see that the pulse is amplitude modulated. On the left-hand side, again, the time axis, it's 200 nanoseconds now. You can see at the beginning, the amplitude is small, and then it increases towards this time center point of the pulse, and then it decreases again. So the overall amplitude is indicated in this very faint gray outline. And then the actual driver signals that are used to generate the pulse are shown in blue and in red. I stands for the in-phase signal and Q for the quadrature signal. In the middle panel, you see now the frequency modulation. And now it's not a flat line anymore. We're starting out at 0 microseconds at the beginning with a frequency of -100 megahertz. And then it stays constant for a while and then slowly ramps up, goes through 0 at the center of the pulse, keeps increasing, and ends up at +100 megahertz at the end of the pulse. So the combination of this type of amplitude modulation with this type of frequency sweep during the pulse generates an excitation profile that now looks almost rectangular. What does this actually mean? So here we have the frequency offset from the pulse, and you can see on the vertical plotted is now the Z component of the magnetization. If it's +1, it means the spin points up, and if it's -1, it means the spin points down. Okay, so now you can see that every spin within ±100 megahertz of that carrier frequency is actually flipped, inverted. It has experienced a 180-degree flip. I mean, anything outside that excitation bandwidth is still spin up, so it's flat and unexcited. With this type of frequency and amplitude modulation, you can really nicely excite a very narrow band and excite everything within that band and basically nothing outside of that band. That's why this type of pulse, a hyperbolic secant pulse, is very popular in pulse EPR spectroscopy. So this is how pulse works. And let's maybe briefly go to the documentation and see where you can look at that. There is a user guide on shaped pulses, which is down here in the section on pulse simulations. And there's also the reference page for the pulse function, which is here in the section on the core functions. On the reference page of the pulse function, you can see all the types listed: rectangular, Gaussian, sync, half sine, quarter sine, hyperbolic secant, worst, Gaussian cascade, and Fourier series. And for frequency, that's for amplitude modulations. And for frequency modulations, you can have a linear chirp, hyperbolic tangent, or uniform quality factor, uniform Q. So this is actually a quite deep topic. We're not going to get into much detail, but if you scroll down, there are some references given as well. And also all the equations are listed on the Pulse website. So you can totally understand by looking at this what is actually being calculated and what these various pulse parameters mean, like the beta. All right. Now let's continue this here. We can not just call pulse and have it plotted for us, but we can have it return us the data, and then we can do the plots. And let's show you how this works. We can ask pulse to return let's run pulse again with just the plotting. We can ask pulse to return us the data from the left-hand side. Basically, the time dependence of the amplitude that we would have to feed into the spectrometer to generate this type of pulse. So we ask for the time axis, t, and for the in-phase and quadrature signal needed, IQ. And we just say again, pulse, comma, hs. Right, if you run this now, we can see in our workspace browser that we have now two vectors, a t vector that is just 401 elements long, and an IQ vector that's also 400 elements long, and it's complex. So the real part of that signal is the I signal, and the Q, the complex, the imaginary part is the Q signal. So let's plot it. Again, we're gonna make two plots next to each other. We're gonna plot t and the real part of the IQ signal, and then t and then the imaginary part of the IQ signal. I'm going to plot this on the left-hand side. And on the right-hand side, let's plot the excitation profile. There is an EasySpin function that takes this IQ signal and calculates the excitation function. And the function is called Excite Profile. It features t and IQ to it. And in return, we'll get a frequency axis, let's call it f, and demagnetization trajectory, let's call it m. We can now start subplot 1, 2, 2, and there plot the frequency axis and then the x component, which is the first row of m. Again, the frequency axis and then the second row of m, the frequency axis, and the third row of m. If you're new to MATLAB and this notation doesn't look familiar, is not intelligible to you, it's actually, this is how it works. So if M is a matrix, then you can specify a row index and a column index to pick out single matrix elements. If you only give a row index and you put a colon into the column index, it will just pick the entire row. So if I put a 3 here for the row index and nothing, or a colon for the second one here, it will just pick the third row. And this here then consequently means the second row, and this is the first row. So this is taking slices out of matrices. And this is a pretty powerful, very compact syntax. And it's pretty natural once you're used to it. All right, let's press Control Enter. And here we go. We do have two plots next to each other. Left-hand side are the two driver functions that are needed to generate this pulse. In blue is the in-phase part, and in red the quadrature part. And on the right-hand side, we have the excitation profile. The x-axis is the frequency offset, and the vertical axis is the +1, and it goes the magnetization component from +1 to -1. You can see it looks more messy than before, but if you delete the X component, which is the blue one, we can select that here by clicking the arrow button on the toolbar, and then select the blue trace and press delete. And then we also click on the red trace and press delete. We're left with the orange one, and that is the Z component, and shows you that we indeed still have that very selective inversion over a bandwidth of about 200 megahertz, which is a large bandwidth. So this is how pulse works, how you can get the pulse information out, and how you can use Excite Profile to calculate and then plot the excitation profile. Now let's utilize these shade pulses in a pulse simulation. What I'm going to do here is I'm going to just copy some code here. We're going to start out with clearing everything up. We're going to define again a nitroxide radical with a G tensor and an A tensor and a 14N nitrogen nucleus, and some broadening of 5 millitesla. and we're going to be at X band. Let's look at this spectrum. Here you can see the absorption spectrum of a nitroxide radical. Okay, and this is a frequency-dependent spectrum. Again, you know, usually when you do pulse EPR, we perform a pulse EPR experiment at a fixed field. And so if you want to understand what you're doing at that fixed field, it's important to first look at the EPR spectrum at that fixed field as a function of frequency. And so you can see that the spectrum, this nitroxide spectrum, extends over about 200 megahertz from 9 to 9.2 gigahertz, and it has a strong peak at around 9.1 something. Okay. Now, next we need to define a pulse. We're going to define several pulses. We're going to do a two-pulse experiment. Right. So first we're going to define a 90-degree pulse. Let's make it 20 nanoseconds long, and we're going to set its frequency offset to 0. Next, we're also going to set the pulse 90 flip angle to 90 degrees. Then pulse 180. Pulse 180, I'm going to set the equal to pulse 90, so as to copy all the parameters over, so we make it same center frequency and same length, except that we need to change the flip angle. We set it to pi. Finally, we have to specify a tau value, let's say half a microsecond, and then we can specify the sequence. The experiment.sequence equals, and then as we saw yesterday, we have to use curly braces. I'm going to put a pulse at 90 degrees, then a tau value, a pulse at 180 degrees, then another tau value, and we should add the delay of the first pulse divided by 2, because that's where the actual echo maximum is, if you want to be correct. Okay, now we would like to excite at the spectral maximum, which is about 9.12 megahertz. So it sets the microwave frequency to 9.12, and the field to the same field we've used to simulate the spectrum we're just showing, the EPR spectrum. So this way we're going to now apply a 20 nanosecond two-pulse echo sequence at this position. And since we're taking 20 nanoseconds, if we're taking a finite length of a pulse, this will result in a finite excitation bandwidth, as it will be internally calculated. Finally, EPRs our echo are usually detected by integrating over the echo, and that's what you can do with EasySpin as well. You can specify a detection window, det window, and we say we're gonna go plus minus 30 nanoseconds relative to that last point in the sequence. So this is again in microseconds, and the first number is the starting point of the integration window, and the second point is the end point of the integration window for the echo. I think finally we need to make sure we get some good powder averaging. So I think 20 knots should be sufficient for this. We can now calculate the signal with Saffron. Saffron is the function that does all the pulse calculations. So it can handle not just the ideal pulses we talked about yesterday, but also these limited excitation bandwidth pulses, or sometimes called real pulses, that we just talked about in this session. So Saffron, you feed in the system, the experiment, and the options. Okay, we need to start running this. This might take a while because my laptop is pretty taken up with this streaming. So while this is running, we can start plotting the signal. We can write the code for it. We're going to plot t comma signal. We're going to put an X label onto it. Let's say t in microseconds, and a Y label for the signal in arbitrary units, which is basically the integrated echo. Actually, it will not integrate. Actually, this is just a transient detection, as we'll see. Echo amplitude. So the detection window shows just over which window we want to observe the echo. So this is no integration yet, just transient. Okay, so this is how you set up Saffron with a custom pulse sequence that accommodates custom pulses that can be chirped and amplitude modulated at your as you want. Right. So you can add now frequency chirps to this in the same fashion as we did before for the pulse function. Internally, Saffron calls the pulse function to get the I and Q signals to simulate the spin dynamics. All right, so while this is running, we should maybe look over to the documentation once more and see where you can find how to do these simulations. In the section of pulse simulations here, there is one section on pulse EPR with real pulses. That is something that it's worth looking at. And of course, there's also the Saffron function documentation by itself. I think the calculation is done. Let's dock this again and run the plotting. And it actually warns me that it's not plotting the imaginary parts. The reason is that it did an IQ detection, a quadrature detection. And here it's basically showing over a range of minus 30 nanoseconds to plus 30 nanoseconds the shape of the echo that's being observed from this nitroxide radical that we've seen the EPR spectrum before. All right, so this is how you would use Saffron to simulate a custom pulse sequence. The third function I would briefly mention in this session, if you still have time, yeah, we do, is Spidion. Spidion is a more advanced pulse EPR function that allows you to specify things like the exact detection operator you want to have, and so on. And here's how it works. Clear everything out. Let's start out, let's make a pulse. Let's say we want to just investigate the spin dynamics that happens during a microwave pulse. Let's define a pulse, and I'm just going to copy paste a pulse definition here. This pulse is called a versed pulse. And the versed amplitude is essentially just a soft on-ramp, then a flat amplitude, and a soft down-ramp at the end of the pulse. And linear means we do a linear frequency chirp. So we're starting at one frequency at the beginning and then just linearly ramp it up or down to the target frequency at the end. The length of the pulse is going to be 100 nanoseconds or 0.1 microseconds. The frequency chirp goes from plus 150 megahertz to negative 150 megahertz. So we're going to cover 300 megahertz in 100 nanoseconds. And then the versed shape takes a parameter. In this case, we use 8, and the flip angle is pi. Next, we're going to define this experiment we want to do in the XPlot sequence. It's just a single pulse. We just want to look at this one pulse and see what happens during the pulse. And we're going to run this experiment at a microwave frequency of 9.1 gigahertz. Now, we still have to define the spin system. Spidion is a function that's more intended for fundamental spin physics investigations. So it has some additional features for the spin system. And one of them is just you can specify the Zeeman frequency right away. Sys.Zeeman frequency is 9.150 in gigahertz. No need to give a G value, no need to give a magnetic field. You just give the actual Zeeman frequency. So this is a function that's not very useful for applying it to specific systems, but is useful for investigating the spin physics. Finally, let's specify some detection operators which you can choose freely, Z1 plus 1. So this would basically mean the Z component for the first spin and the plus component for the first spin. And also the detection frequency. We can change the direction frequency. Let's do 0 for the Z component and 9.1 to down convert the kind of rotating plus 1 coherence to the from 9.1 gigahertz down to 0. All right, now we can run the simulation. T comma signal equals Spidion sys comma exp, and we could run it. So we press Control Enter. This should be actually fairly fast. If I got everything right, yep, now it's done. Spidion is actually an EasySpin function. Is a fairly recent addition. It is the result of the PhD of Stefan Pribiter, who is sitting here behind the scenes managing all the technology. And it has been integrated into EasySpin. Okay, now we've got the simulation. Let's plot it. For example, what we could do, we could plot the time axis, and let's actually multiply it by 1,000 to get the nanoseconds, and plot the real part of the signal. And voila. Now we can see that we see two parts. We ask for two detection operators, right? The Z component and the plus component for the first spin. And the Z component you can see is in blue. It starts out at -1 and then slowly gets inverted up to +1. And the plus component has an oscillatory behavior, but basically stays around 0. We can plot this a little better by plotting it this way. I'm going to just copy the code up from here in 3 dimensions. Let's do axis equal as well. What I've done here now, actually maybe grid on. What I've done here now, I've plotted the actual spin vector, basically the X, Y, and Z component of where the spin is pointing at every time during the pulse. And as you can see, we're starting out at the very bottom, so spin down and then slowly spiraling up during the pulse until we end up in the plus Z direction. And I want to remind you that the microwave frequency is at 9.1 gigahertz, but the spin frequency is at 9.15 gigahertz. So this spin is actually 50 megahertz off resonant from the microwave frequency. It has a higher frequency than what we're shooting into the sample. But due to the construction of this pulse, even this off-resonance spin that's 50 megahertz off is nicely inverted and sees a full 180-degree spin flip. And Spidion allows you to look into the exact trajectories these spins undergo during a pulse. So it's definitely a function for the more advanced users among you, especially those who are involved in designing new pulses and new pulse sequences. If you go to the EasySpin folder, I'm going to fire that up. If you go to your EasySpin folder, you will have 3 subfolders. One is EasySpin that contains the actual code. One has the documentation, all the documentation. And the third subfolder is actually really important for those who are getting started using certain parts of EasySpin. It's examples, and it contains a ton of subfolders that have a lot of examples that help you see how specific functions in EasySpin can be used. And there's 4 different subfolders for Pulse EPR. One is on using the function evolve, which I haven't talked about, then one for saffron, one for pulse shaping, and one for Spidion. And each of those, we have a series of examples. Just go in there and dig around and see if those things make sense. And maybe you can use some of these scripts as starting points for your own scripts that are relevant for your research. Okay, I think this brings me to the end of this session on pulse shaping. And we'll have a small break. According to the schedule, we're starting at 9:30, which is in 11 minutes. And as I mentioned, we're going to first talk about Orca interfacing and about Curry, which is a function to do magnetometry in the next session. And in the 2 sessions after, we talk about broadening, high-order spin operators, coupled spins, trajectory simulations, and some behind the scenes of EasySpin. So see you in about 11 minutes.